This is Brian Putt. This is part 2 of a video that's talking about using Excel to flip conditional probability trees. In the last video, we showed how to take this 2x2 conditional probability matrix and flip it down here manually. Now what we want to do is to take this larger matrix that's asymmetrical and convert that using Excel. So let's flip over to our model and see how to do that. Here is our conditional probability matrix with reality shown over here and the indicators shown here with these probabilities shown on this PowerPoint slide, totaling 100% with these probabilities for reality. To solve this using SIP math, we need to calculate the cumulative probabilities, starting with 0 here and then summing up the probabilities this way. Similarly, for these conditional probabilities, we want to do the same thing. And now we're ready to start building our model. This is going to be a SIP math model. So the first thing we need to do is to initialize. So I'm going to go over to my SIP math modeler tools and I'm going to initialize. And in this particular simulation, I'm going to run 10,000 iterations. Okay? And when we initialized with SIP math, it generated 2 additional worksheets, PM table and the PM math chart data. Now what we want to do is sample from reality. I'm going to need a random number for the sample, and I'm going to establish a seed here so I have some better control over what the random number is, and I could test different seeds to see if it really makes that much difference. So let's go get a random number which is uniform. So I'm going to generate an input. I'm going to generate a uniform. And we're going to specify the seed as being right here. Okay. And we'll need to give it a number. Let's just give it 10. And now, what is actually sampled for reality? Well, if I take this random number and looked it up on the Q probability chart, it would tell me which of these actually happened. And so in this case, 0.96 is bigger than 0.75, so this should be reality C. We'll use the lookup command here, equals lookup, and we're going to look up this number in this cumulative probability, and we'll pick this answer. So there's reality C. Over here, we'll use the match command to determine which row this is in. Say equals match. Look up this value in this, and it's row 3. Now, having identified the reality is C, we now need to do a sample. We're going to need another random number for that. So over here we'll generate input, uniform, give a starting value over here, and we're okay, and we'll call this 20. Okay, so for reality C, if I got a value of 0.3, 0.3 is more than this and less than that. So I think the answer should be, indicates B. A number of ways to do this, but the shortest way to do this is this way. Equals match, and I'm going to match this number, and then I really want to pick this array because we're in reality C. And I can do it this way. I can type an index command and pick this whole array, and we want the third row, and then we want to use the whole vector. So I'm just going to put a 0 there. Okay. I need to end the match command, and it came back with a 2, which is that 15%. Now, what was the sampled indicator? The sample indicator is actually indicator B. We'll use an equals index command of this array, comma, kind of hidden here, just do it that way, indicates B. Now we need to calculate a conditional metric. That conditional metric is going to tell us which row and column we're in our joint occurrences. The way I'm going to do that, I'm going to set this equal to the reality times 10 plus the indicator. That'll give us a unique metric for each one of the outcomes. Now we're going to treat the reality and the indicator as being outputs. So let's give these some names. D underscore reality and D underscore indicator, and we'll call this D underscore metric. How about that? And as you remember, the D is used to reflect that this is going to be a distribution. It's not going to be a scalar. We'll use our SIP-Math modeler tools to define these as outputs. So I'll go to define outputs, click on this, and I do not want sparklines. And we'll do the same thing here. And one more time. And we have our three variables in the simulation shown here. I might add that if these had all been contiguous, so no blank rows in here, I could have done those all at the same time. So now down here I have the matrix of the joint occurrences. So what I really want to know is how many times did I get a 1 times 10 plus 1 or an 11 in my D metric. We're going to do equals count if, and I'm just going to type in D metric because that's the vector I want to look at. Count if that range is equal to this times 10 plus this number here. And it's told me I've got let's change the format of that. We'll just call that a comma with no decimals. So out of my 10,000 iterations, 4,235 said reality. When it was reality, it indicated A, or actually it's the joint probability of reality and indicating A. And we saw that reality up here had a 60% probability, and I was going to be right 70% of the times. So that's going to be my biggest number. Now I can copy that across here, but first I need to hold the B constant, and I need to hold the 18 constant, and then I will copy that over here, paste formulas. Alright, now the total here, and you see I have 10,000 outcomes. Let's also get the total here equals the sum of these. Perfect. Having those numbers, how do I get the probabilities? Well, first of all, what's the probability of getting an A? It's equal to this number divided by my 10,000. Hold that constant, copy that across. And of course, the sum of those, I have to have an indicator, so that should be 100%. Now, given that the result was indication A, what is the probability of getting A, B, and C? This is equal to the number of occurrences here divided by how often did I get A. We'll call that percentage. And what we need to do here is we need to hold the 23 constant. And then we can copy that over here. So we'll get the totals here. And we see that these are the Bayesian probabilities. If I'm given an indicator, what is the probability of reality? If it indicates B, the probability of actually having B is 35%. There's a 23% chance the reality is C. You can see there's an 11% chance that the indication is they don't know. So let's compare the two outcomes. This was our original matrix, and after flipping it, here is the result. It doesn't look anything like this, and there's no way that you're going to intuitively come up with these probabilities. SIPMath has allowed me to take this matrix and invert it fairly easily, and I could go into my model and change these probabilities and automatically get the new conditional probabilities indicator reality. How are these then going to be used in any analysis? Well, we're going to put them into a decision tree, presumably, where I'm going to get my indicator, and then I'm going to make a different decision, or possibly make a different decision, depending upon that indicator. That's why I've got 4 different decision nodes here. And then after I make my decision, I will see what reality is. So these probabilities here are going to depend upon which of these indicators are given. So where to get more information? You might wish to view my video, Value of Information with Imperfect Information. There's also information on probabilitymanagement.org. There's some videos on that site. You might want to review the tabs that are highlighted below here, like SIPMath free downloads and models. You might want to look through the book The Flaw of Averages by Sam Savage, and you can contact me through LinkedIn, and I can send you some additional materials. Hope you found these 2 videos valuable. Thank you.